midterm 2. So this is just a review session. So we're going to go over some stuff. Now, what we did in the first class, I think we'll do in this class as well. Kind of a nice format. You know how last time we went over 2 topics and it kind of covered the whole time? In the morning we went over 1 topic, and in the second half,
broken.
questions that people were curious about and stuff. And I think that format went well, so we'll probably do that. So basically there's 4 major topics in this part of the course. Remember, it's a non-cumulative midterm tomorrow. So it's just stuff after midterm 1. So we did some circuit stuff, some magnetic field stuff, the foundational equations like Ampere's law, Faraday's law, then we did the inductance generator stuff. So there's 4 options to vote for. So we'll just get straight to a vote. Kind of like last time, you get 1 vote. What do you want to kind of go back over? What's the topic you find the most challenging? It was a tight vote in the morning class. I'll tell you that. I won't say what yet. So we'll go in chronological order. Who wants to go over the circuit stuff we did at the start? No votes. Same with the morning. That's crickets. That's 0 votes for the entire topic. So hopefully you're good for the circuit stuff. What about the magnetic field stuff, like Biot-Savart law, magnetic field due to point charge? Any votes there? No. Okay, so similar to this morning, it was a pretty tight vote between the other 2 options. So your options are Ampere's law, Faraday law type stuff, like the foundational equations of electromagnetism, or the inductance generator type stuff. So please just vote once. We'll start with the Ampere Faraday stuff. Who wants to go over that? So keep your hands up. We can actually count. We had to do a recount this morning, so I'm just going to go ahead and count the first time. Okay, pretty good. And then who wants to do the generator inductance type stuff? See, the same thing, it's so hard to count. Okay, so here's what I'll say. It's extremely close. In the morning, we ended up doing inductance. So I can go either way. It's pretty similar stuff, like the Faraday law inductance type stuff. If you want, I can try and do it. Would you rather I go in depth into one of them or kind of loosely over both of them? Option number 2. I see a lot of juices out there. We're all right. I'm just going to sit down. We're chilling today. It's casual today, so we're going to go over some stuff. So I'm not surprised because I agree that maybe some of the most conceptually difficult stuff in the course is related to this Faraday's law type stuff. It's super fascinating, right? It's really cool stuff. It's just a lot to wrap your head around at first. So what I'm going to do, I'm going to try and go over what I think is like the big picture, important, absolute minimum you should understand about this type of stuff. You could go through some of the technical details line by line later. We're not going to sit and go through line by line like we did in the lecture. I'm going to talk kind of big picture about these topics, okay? So Faraday's law, it's this thing here, and basically it tells us that this is the magnetic flux integral. The negative change in the magnetic flux is always equal to the electric field going around that region we calculated the flux through. Okay, so the statement of Faraday's law is that a changing magnetic field produces an electric field. All right, so that's please at minimum know that coming into this exam, right? That what Faraday's law tells us, changing magnetic field produces an electric field. This gives us a new way we can make electric fields. Now, one of the first things we talked about in this lecture, let's talk about this was the experiment we did in class, because there's 4 of these experiments. I had some questions about what would you want to know about this. I'm not someone who's going to ask you, what date did this happen? Or which one of these experiments was the second induction experiment? I'm not going to be asking you stuff like that, okay? So I wouldn't worry about the dates or or specifically which one was which. What you should know is the big picture of what did these experiments do, right? This told us if we move a magnet in the coil, which we now interpret changing the magnetic flux in the coil, we induce an EMF, induce a current through this circuit, we measure a current by moving this magnet through the coil. So that's pretty cool in class, right? One of my favorite demos to bring in was talking about this one. But all of these experiments play with that same basic idea. Like here, we learned that you don't actually have to move the magnet, you can move the coil and make a current. Therefore, we had the very important insight that it's the relative motion of the magnet in the coil, not that you have to move the magnet. So the magnet and coil have to be moving relative to one another in order to induce a current in the wires. And then we also saw other experiments like this one, where you could change the current in this one, produce a magnetic field that's changing. Now we have a changing magnetic field in this one that ends up producing a current in this circuit. This is kind of like what we end up talking about for mutual inductance, right? Which is that you can align two coils, change the current in one, change a magnetic field in the other, and create this kind of magic current here, which is the basic idea behind stuff like transformers, right? So these experiments are very historically important to figure this stuff out. Then in this lecture, we just talked a bit about magnetic flux, the basic ideas, which is that you have some surface, the dA vectors are always pointing perpendicular, the B vectors are pointing at some angle relative to the surface. You basically take the dot product of B and dA, add it up over the whole surface, that is flux. But one of the key insights in Faraday's law, magnetic flux is not enough to make this happen. It has to be a changing magnetic flux. So you need not only a magnetic flux, but this flux has to be changing in order to induce the electric fields and so forth. So what we then talked about is stuff like this, how our electric field, maybe I'll go to this figure, I think this is a nice one here. We talked about how if we change our magnetic field, represented by these arrows here, we have an electric field looping around if the magnetic field is in one direction. The electric field that is induced loops around. And you can use this to conceptually understand why we make an induced current in a solenoid. You can picture in here, if we increase the magnetic field in here, there's going to be an electric field looping around in the coil, putting a force on the charges, causing a current to flow. Okay, so essentially what we did is we first talked about Faraday's law and how changing a magnetic field produces an electric field. Then we said, okay, now we can use that electric field to cause a current to flow in a circuit and basically make currents by changing magnetic fields, which eventually led to our principles of modern day power generation. Finally, we did an example here for Faraday's law. This is really the only example we did in terms of using the integral form of Faraday's law, where we said, let's have a Faradian loop, some circle here. We want to find the magnitude of the electric field anywhere on the circle due to the changing magnetic field going into the board. And there were some difficult conceptual ideas here, like, well, where do we place the circle? And we said that we have to place the circle kind of at the center of the magnetic fields. You can't just place it wherever you want. It has to be centrally symmetric for this to work out nicely. It's always true. Just like Gauss's law, Faraday's law is always true, but we wanted to make a nice, simple example we could calculate with. That's very difficult to do, which is why we did this one and this one only. Okay? So that's the Faraday's law lecture. Any follow-up questions of things in this lecture specifically you wanted to touch on before we go on to inductance? Follow-up questions here. Okay, cool. So let's keep this Faraday's law journey going, because essentially lecture 20 we did Faraday's law, but lectures 21 and 22 are just applications of Faraday's law. Right? When we go on to inductance, we basically did a whole lecture on this idea that coils can cause changing magnetic fields in themselves, in each other. Those create EMFs that cause currents to flow. So it's a very complicated situation, not easy to understand. Basically, we take Faraday's law and we write it in this more compact form here, where the left-hand side we call the induced EMF, and the right-hand side we call the magnetic flux. So the induced EMF is equal to the negative change in magnetic flux. This is a form we used for our mutual and self-inductance equations. In a nutshell, what we did in this lecture, we took this equation here, equation 5, and said, if the EMF is due to a flux created by another coil, what is that EMF due to the change in current in the other coil? Or, if the EMF is due to the change in flux in yourself, what is the EMF due to the change in current in yourself? That's mutual and self-inductance in a nutshell. So, we also did this stuff. I think some of you have been having difficulties with this, which makes sense. It's not an easy idea. So I'm going to go through one of these because I figure, thumbs up if I'm going to go through one of these, just because I figured that this has been a common question I've been getting. This is a very involved situation, these diagrams, but they're basically the only 4 dynamic situations we can consider. It doesn't have to be a magnet. The basic idea here is, what's the magnetic flux inside of our coil, or of our ring of wire here? We're just using a magnet to have a practical idea of how we would make this field happen. So you could take a magnet, you could either move the north end closer or pull it away. You could move the south end closer or pull it away. In each of those scenarios, the magnetic flux inside is changing, right? Therefore, there's an electric field looping around, causing a current to go. And that current is moving charges, which makes another magnetic field contribution. So you have the magnetic field from the magnet. It makes a current flow. That makes another magnetic field contribution. And you can imagine this is a very complex dynamic scenario. Why we introduce these diagrams is to ask ourselves the question, which way does the current flow, and which way is the field made by that current, which is kind of one and the same question. This can all be explained by Lenz's law, so we can explain all these diagrams conceptually without having to do any math. So we're going to talk about number A, maybe number B. So number A here, the north end, we know vectors point out of the north into the south. So the vectors in this loop here are getting bigger and bigger as we move the magnet closer. That means the flux is increasing downwards. According to Lenz's law, we always have to oppose the change. So our current is going to flow such that the induced B, which is this arrow here, is opposing the change. So we want an induced B up. If you go back to our ring of charge or ring of current stuff, there's a right-hand rule. Thumb points in the direction of the field, fingers in the direction of the current. So if you know in figure A, use your right-hand rule, your thumb has to point up to oppose the change, your fingers tell you the appropriate direction of current. Okay? By the same logic, all of these figures, based on what you're doing with the magnet, you can figure out which way does the current flow, which way does the induced B point. Let's talk about one more here, figure D. Now the south end is getting closer. That means the flux in our loop is getting bigger in the upwards direction. So our current has to flow such that the induced B opposes that change. So we make the field downwards. Using the right-hand rule, our current has to flow in the opposite direction. Okay? Any questions about these? I know these are kind of a tougher concept here. So these here, there's more basic versions of this on the next slide. This could be a magnet. Basically, the solid arrows are the increasing or decreasing field, and the dashed arrow is the induced field. So here's all the possible scenarios of if you have a magnetic field through a loop. Is it increasing or decreasing or staying the same, and which way is it going? If you can conceptually figure out all these, that's really all the possible scenarios. Okay, so I recommend going through these, making sure you can do those. Anyway, I want to talk about mutual and self-inductance. Mutual and self-inductance. This coil, coil 1, if we change the current in it, we will have a changing magnetic field from it that will extend into another coil if it's side by side. Now in the other coil, we have a changing magnetic flux. What does that mean? That means that this coil, according to Faraday's law, will have an induced EMF and current will start to flow over here. Same thing in reverse. If we change the current here, we induce an EMF here. And same thing on themselves. If you change your current in coil 1, there's a change in flux in coil 1, inducing an EMF in itself, which is impacting the situation. This is a very dynamic and complex scenario where these coils impact each other and themselves. Combining that is the stuff about transformers at the end. What we did in a lot of this lecture is kind of figure out how do you define the induced EMF in this coil due to this coil and vice versa. Why was that a process? Well, we know Faraday's law says the EMF is due to the negative change in flux. But what we want is what is the EMF in one coil due to the change in current in the other coil. That's just a lot easier to work with in practice. If you have two coils, you're changing the current in one, you can figure out the induced EMF in the other. That's way easier than working with flux. So we did a lot of work to figure that out. How did we do it? Well, we introduced, for flux, we said, okay, we know the flux in one coil is due to the change in current in the other coil. We don't know how exactly they're proportional, so let's just put in some random proportionality constant, C. Then we plug that flux back in. We can write Faraday's law in terms of current instead of flux. We have a couple constants, the number of turns in that random C. We just package them together and call it mutual inductance, which is a property of two coils, how big they are, how they're separated, that sort of thing. Just tells you about that relationship between the two coils. And if you do the same thing in reverse, you end up getting the same value for this M. Okay, so basically we take Faraday's law, replace the flux with current, and we're left with this set of equations here, which is the induced EMF in one coil due to the change in current in the other, and vice versa. The constant in that expression, M, mutual inductance, it's the same for both of them in either direction. Okay, so these equations here, the mutual inductance equations, very important for transformers, for example. Also, we did some examples here. If you want to use these, we're going to have to take the time derivative of a function. So if you have the EMF in coil 2, and you know the change in current in coil 1, you would take a time derivative in order to figure that out. So what did that look like? We did some examples where, okay, here's some functions that you can plug into the d/dt relationship. So you take some time derivatives, multiply it by negative m, you're left with the induced EMF in one coil due to the change in current in the other coil. So these are very real values that we would figure out in order to say, what's the induced EMF in the second coil that ends up powering that second current or second circuit, kind of like a battery would for our prior EMF discussions. So we also did this, talk about the same thing for the self-inductance. This is more complicated. We'll talk about these more in part 3 of the course. So we just kind of briefly introduce this for now. Basically, if you change a current in just a single coil, the property of inductance happens on itself. Because it's making a changing magnetic field, according to Faraday's law, that makes a changing electric field. It starts impacting itself, and according to Lenz's law, working against itself, basically, in this process. It's a very complex phenomena, but the math is the same as the mutual inductance case. The induced EMF in the coil itself is due to its self-inductance times the time driven of its own current. Okay, so this is the self-inductance relationship. Finally, we put it all together with transformers, where we talk about these ideal transformers, where we have two coils, we induce an EMF mutually and on themselves, and that's what the transformer equations are. You just add the self and mutual for each of them. And what we did is we said, okay, let's just talk in terms of the flux relationship from earlier in the lecture, equate those d phi dt's, and we can get some relationships for how we can draw voltage using a transformer, right? So this was the inductance lecture. Any follow-up questions on this one here before we do a brief overview of generators? Yeah.
You mentioned for the mutual inductance examples, like you gave us a function, you give us the derivative as well. What would the question look like? Would we just like simply be multiplying that by negative m, or?
Yeah, I mean, you might have to take the derivative yourself if you were given a question like that, right? But yeah, if you can take the derivative, beyond that, it's just negative m times that derivative. Okay. So it wouldn't be. I wouldn't like do something random we hadn't done before, like figure out the mutual inductance constant based on some scenario or something like that. Right? It'd be more based on the types of stuff we talked about. Cool. Okay. Now, anything specific you want to talk about from the generators type stuff? Both of you are doing this. I don't know what that means. You did that and then he did that. So you just copied you. Word. Okay. So, anything specific in this lecture? We could talk about slide wires. We could talk about alternators. We could talk about power generation. Any suggestions yet? The slide wire? That sound good to everyone? The slide wires, thumbs up, maybe? Okay, let's talk about slide wires. Okay, so the basic idea here is if we have this wire in a magnetic field and we move it, so the magnetic field here is just some field going to the board. We have, this could be like a hunk of copper or something, and we move it this way according to this velocity vector. This charge is going to experience a magnetic force moving it upwards. When we separate our positive charges up here and negative charge down here, we make an electric field pointing from here to here, wanting to force it downwards. So there's going to be a magnetic force up, an electric force down, and by creating an electric field, we also create a potential difference, right? Because the potential difference is deep down just an electric field between these 2 points. So what happened is if we attach this piece of wire to this curved wire, and we move it, we create a potential difference here, which can be used to cause a current to flow in the wire, just like a battery would. And this is just like what we would do with our other generators. We want to use motion related to magnetic fields and wires to cause currents to flow. Right? So this is the basic idea of the slide wire example we did. Now, we actually did 3 cases in class. I don't know if there's a specific one you want to go over, but I'll kind of overview them conceptually. The first one is we could use our delta V equations from part 1 of the course to calculate, based on the electric field in here, what is delta V between point A and point B. We did that. we got QVB. Then we introduced something called motional EMF, which is the EMF due to the motion of a wire in a field. We used that expression, we got QVB. Finally, we said let's interpret this using the flux interpretation of Faraday's law, where the magnetic flux is increasing here as we move this. What is the induced EMF? We did that calculation, we got QVB, anyway, we got QVB again. Okay, so we got QVB any of the methods we chose. Is there any one of those in particular you want to chat about? All of them?
Do we need to do all three?
Is all of them vote? How about hands up for all of them? Hands up for just the delta V. Hands up for just the motional EMF. Hands up for just the induced EMF. Okay, so all of them is clearly the situation. Okay. Basically, the delta V ones we'll go over really quickly. Delta V is the integral of E dot dl. But along our wire, E and dl are parallel. So E dot dl, the magnitude would just be E dl here if we do this calculation, just like we do with Gauss ampere type stuff. E is a constant magnitude, we're saying, which we'll be able to pull out of the integral. Just have E times adding up the length of our slide wire, which is length L. We plug that back in, and what we had said is this thing's in equilibrium, where E equals VB, just like our velocity selector. So we can plug in E equals VB. We're left with that the potential difference is VBL in that slide wire. And so this was our first approach, is we just used the delta V equation from before to figure out what is the potential difference across that wire. Then we basically did the exact same question from two different other perspectives. Let's move on to motional EMF. This was a new thing we introduced this lecture, which is that the motional EMF is the calculation of this integral, which is quite an anti-chill one as far as ones go in this course, because we have to take a cross product, then a dot product, then add it up over the whole loop. So we have to take a cross product of V cross B at every point on the wire, then take a dot product of DL at every point on the wire, and add it all up over the whole loop. That's what we call motional EMF. Turns out this is the same thing deep down as the other ones. It's just a different way we can calculate it. Why would we introduce this? Well, when you're doing things in practice, you might not want to talk in terms of flux. You might want to talk in terms of the motion of your generator and stuff like that. So this might actually be more common in practice than the flux calculations we do. Anyway, what do? We go back to our slide wire. We define a velocity vector using our right-handed coordinate system. So positive x is this way. We have negative z into the board. So we define our V and B from our diagram and take a cross product. Then we define a DL going in the positive y direction. We take the dot product of that cross product, and what we're left with is VB dy is going to be the integrand for our motional EMF. So we plug that back in to the definition we had. It chills it out quite a bit, right? It chills it out down to just, we have to add up VB dy, but V and B are constants, so we pull it out. We have VB times adding up the entire length of our wire, which we've already said is DL. We have VBL from the motional EMF. So we end up with the same result for motional EMF as we had for delta V. The final interpretation was the flux interpretation, where we have to literally calculate the flux using our dA vectors and B vectors and our DL vectors going around the loop, according to Faraday's law. This is when I talked a bit about orientation. I'll talk about it a bit here just because it's a complicated concept. Basically, if you have an open surface, it's ambiguous which way dA points. Right? If you have a sphere and you say that dA always points outward from a closed object, you always know dA is pointing out. If you have a hula hoop, and let's say the hula hoop is here, I should have brought, it's still in my office. The hula hoop is right here, okay? And this stick is the dA vector. Is it pointing towards you or away from you? Now you have a bit of a choice there. Additionally, is the dL vector going counterclockwise or clockwise? You have a bit of a choice there. If you keep one the same and flip the other, you get a different answer. So it basically, you need to be consistent with which way you point dA versus dL. That's all based on a right-hand rule. So the direction the dA points, which is out of the board here, has to be consistent with the direction of dL, which our fingers would tell us as being counterclockwise here. If we flip it, which we do later in the lecture, dA into the board, dL has to go in the opposite direction. Essentially, all of these equations, like Faraday's law in 204, are developed with a specific orientation in mind. You could adopt the opposite orientation, but then you'd have to change every single integral of the vector that has been defined, because it's all based on that same orientation. Okay, so use the right-hand rule, you can relate one to the other, and then it's just like our Gauss-Ampere type problems. We find the flux using the cosine law. dA and B are anti-parallel, so theta is 180, we get a negative sign. Add it up, you're left with the induced EMF is B times dA dt. Remember, we could pull the B out because it was constant everywhere. Area is growing because we're moving our slide wire. We have a time derivative of area here when we do the slide wire generator problem. Then we figure what is that dA dt using our little diagram here. So remember the rectangle formula is L times V dt here in the diagram. So you just rearrange that for dA dt, you plug it in, and it's kind of cool. We still get VLV from this third method. So that's kind of the brief overview of those three things we did. We did do the opposite orientation, which was to flip this dA and dL, which is here. Now dA is in the same direction as B going into the board, and dL is the opposite direction of the induced current. What happens in this case is we get the same result but negative VDL. You can think of this as when you do a Kirchhoff loop, when you go around one way through a battery, like a 9-volt battery, let's say, you could get plus 9 volts. Or if you do your Kirchhoff loop in the other direction, you'd get negative 9 volts. Right? So the direction of the loop you take impacts the sign of the potential difference. You're either going from the plus to the negative end of the element or the negative to the plus end. And that's why flipping the orientation flips the sign here. Right? So what I'll say, I'm going to say any follow-up questions to this generator type stuff. If not, we'll move on to phase 2 here of our little program. Any follow-up questions? Okay, so for our remaining time, I'm going to turn this microphone on, and we're going to do a ask the audience situation. Okay, so this was fun this morning. Basically, any little questions about the exam, content we've been covering, and then we'll just kind of pass the mic around and we'll just answer. So anyone got something here they'd like to ask? Now you're in charge of the mic, so you have to pass it to the next person.
In our last lecture, 22, we went over, I believe it was this lecture, we went over some real life examples. How in depth should we know those for the midterm?
So we went over what examples?
Like, for example, the Niagara Falls example.
Okay, good question. This stuff, very minimal. Like, I was more doing this to give you some context for why you're bothered to learn all this stuff, right? And why it's applicable to engineers and stuff like that. So you should know that hydroelectric power is a way to take mechanical energy and convert it to electrical energy and stuff like that. But I would never ask you, like, what percentage of Canada's power generation is hydroelectric or something? I wouldn't be quizzing you on these little details. It'd be more like the big picture stuff I would expect you to know about this stuff. So I wouldn't stress too much about this thing. All right, next question. got something here? Yeah, right behind you maybe? Oh, no. This is easier this morning because it's such a bigger class. So it's easier. Oh, we got a question back there. Yeah, you got to bring the mic back. You got to bring it back. Let's get it going here. There's no bad questions here. You got the exam tomorrow. What's the harm in asking what's still confusing, right? So if you have any questions, bring it forward. Let's go.
Do you know how much conductivity will be on
Do I know how? Okay, first off, of course I know how much of each topic will be on the exam. I wrote the exam. So rephrase, please.
that? Could we go over conductivity?
Yes. Okay, so I'll briefly go over conductivity here. Remember what lecture exactly you're referring to? Because I think we talked about it.
14? Yeah, 14.
You're talking about conductors, right? Yeah, well, say feel free to take off if you want to go study and stuff. It's super casual here, so if you want to take off, then else whatever, take off at any point. So we're going to talk about conductivity here.
Oh, he has bookmarks.
So this stuff at the end of this lecture, right? Okay, so what I'll say about this stuff, like, and this is a rule of thumb for any topic on these exams. If we very briefly did something, it probably won't be a major topic, right? So like, if we briefly do something in one lecture, you could expect at most one single question assessing it. Now, conductivity, it's just the inverse of resistivity. So you could think of it as being basically a different way to measure the exact same thing. Resistance is how resistive something is to current. Resistivity is that property of the material. Conductivity is the opposite. How easily does something conduct? And conductance is like what resistance was, which is for some specific object. How easily does it let charge go through? So it's just a way of quantifying how good or bad is a material at allowing charge to flow. So something like copper would have a very high conductivity because it's such a good conductor that we use in all our buildings and stuff.
Could you do the torque that happens from dipoles?
Torque from dipoles, for sure. Let's chat about that. All right. So when we talked about, you're talking about the, was it magnetostatics or the next? Maybe it was the next one. Maybe it was current carrying wires. A bit of both, I think. We talked about both. See, this is why I should have brought my hula hoop, right? It would have been nice to have the hula hoop and go over this again. So the basic idea is that if we have some current loop in a magnetic field, the force is equal and opposite. So the field is all pointing up here. The current is looping around. So the force ends up being opposite. It doesn't move side to side. But there's a non-zero torque. This thing is being torqued to align with the field. So basically the force on this side, R cross F, this would be your R, this would be your F. So R cross F, you have a torque there. This would be your R, this would be your F. R cross F, you have a torque in the opposite direction. You would torque to align with the field, such that the area vector and the B vector are in the same direction. In principle, that could be a very difficult calculation. If I kept giving you random loops, and you had to find all the R cross Fs for every side, it'd be a very unreasonable situation. So we can make it a bit more chill by introducing the magnetic dipole moment. If we have any current loop, we can define the magnetic dipole moment as the current in the loop times the area of the loop times the unit normal direction, which is just perpendicular to the loop. Okay? This means we don't have to every time go back and do all those force and torque calculations. We can just do everything using this mu here if we know what it is for a particular dipole. And on a side note, it's of course very important to know that a current loop behaves like what we call a magnetic dipole, just like a bar magnet. So what happens let's say this is our mu vector, which is pointing out of our loop. Our loop is this table, and the field is pointing that way. What happens is a magnetic field torques a dipole so that the mu vector aligns with the field that it's in. So what's happening with the torque, no matter what way you're pointing, you will be torqued to align with the field. Fun fact, this is what we briefly talked about with the electric motors too, at the end of last class. Is that, okay, we torque to align with the field. Now in an electric motor, we flip the direction of the current, then we torque the other way. Then we flip it again, we torque the other way. And we keep flipping the current so we generate motion. Right? So this is also important for the basic idea behind an electric motor. So any follow-up questions about that there? Say that. The energy as well, sure. What happens? Let's talk. R mu aligns with the V external. They're parallel in the same direction. The value for the dot product is what? Not zero. What's parallel to that product? It's at a what value? A min or a max? Which one? Come on. Two vectors in the same direction. It's definitely a max word. Okay. It is indeed a maximum. Mu dot b is a maximum. So what is negative mu dot b? That's a minimum. Physical systems tend to want to minimize their own potential energy. So when you take your mu vector and you align with b, you have now minimized the potential energy. We've reached the minimum of our energy drive, essentially. That's why we settle down there and chill. That way would be max. That would be an unstable equilibrium. That would be like taking a pendulum and trying to balance it upside down. Is the mechanical equivalent of what you just described. Fun fact, I think this is a fact. If you take a pendulum and you like we did before in the course, right? You take a pendulum, its only stable equilibrium, I believe, is straight down. There's what's called an unstable equilibrium, where you could balance it straight up, but any initial condition will permanently destroy that from happening or something like that. It's a pretty cool, it's a cool model to look into, like what happens. You can further take that into something called the chaotic pendulum, where you can talk about 3D pendulums and how they move. It's cool stuff to look into. Anyway, next question. We got a microphone back there. Anyone want the microphone? Got a question going on? Question, anyone? Okay, good. Bring that mic up now. That's the penalty. This is a brutal session, so you get penalized, Frank. You can pass it up. Yeah, pass it up. There we go. Yo, we'll pass the mic up. Mid row, yeah. Mic there. Yeah, you have a question?
There's gonna be.
Can you go over electric potential again?
I was gonna ask that.
Potential difference?
Potential difference. You mean from part one of the course? So this is a good point to mention that this exam tool is non-cumulative.
We don't need that, like, the potential difference in wires.
The only thing you would potentially need it for is like
Potential.
circuit stuff. So you want to go over potential difference in the circuit context or the slide wire context.
Yeah, sure. Some of the questions that I was doing on the practice exam were asking potential difference across a resistor.
Okay, yeah, sure. So you're talking about the circuits lectures at the start of project. Okay, perfect. Yeah. Okay. So do you want to talk about resistors specifically or just generally? Okay, so when we have a circuit, where's our circuit here? When we have a circuit, across every circuit element, we increase or decrease in potential difference. Like the potential on one side of our circuit here will be higher or lower than the other side, right? So essentially, we need expressions for like the magnitude of the potential difference, but more importantly, like whether it's plus or minus is important. Does that make sense? When we talked about delta V in part 1 of the course, it was very strictly like integrating the electric field type stuff. When we move on to circuit theory, we have expressions like Ohm's law, this one here, that's basically what is the magnitude of the delta V across that element. But whether or not we increase or decrease across that element depends on the situation, like which way is our loop going and stuff like that. So effectively what we do is we give you some expressions for what is the delta V across a couple of common elements. And then kind of independently, you have to figure out, is it increasing or decreasing based on some set of laws we've defined. So it's not like you're calculating it like an integral and getting an explicit value you plug in. You're putting in IR and then figuring out the increase or decrease in potential difference based on some rules. Does that make more sense? I think maybe we'll, because in a minute I'm going to wrap up. We can come up and we can like go over one, kind of chat about one of the circuit examples. Is there any final questions before we wrap up here?
Yeah, sure.
Yeah, can you bring the mic over? We can pass them on. Okay, we'll do one more question, then we'll wrap it up. You can come up to the front and we'll chat about stuff.
Could you go over magnetic fields and current loops?
Magnetic and current, so kind of like we were just talking about. Basically,
Sorry.
if you have a current loop here,
The field.
if you use the right-hand rule, you put your thumb in the direction of current, your fingers go through the loop and tell you the way the field's coming out. And you can also effectively use a rule where you put your fingers in the direction of current, your thumb will point in the direction of the magnetic field. And essentially in both cases, we have moving charges. Moving charges make magnetic fields, which is why the loop makes that kind of predictable field. All right, anyway, let's let everyone go here once you get going. Good luck with your exam or exams, plural. We'll see you on Monday for part 3 of the course.